Hi, it's Liz Sneddon. Let's have a look at comparison conclusions. So we've got this idea of our population up top and we've got our sample down the bottom, and we started by taking a sample from our population in order to understand. Now we're going to use that sample information to make an inference about the population. So let's look at a couple of situations. So I can make the call if I can see, like this group here, all of this bottom group is smaller than the other group, and equally all of the top group is bigger than the other group. So because all of one group is bigger than all of the other group, I can confidently say, yes, this group does tend to be bigger than the other group. Let's look at another scenario. What if they're a little bit closer together? So in this case, I've got all of this bit, so lots of this group. You'll notice I haven't coloured in the red for the top tail, but lots of that data is smaller than the other group. Equally, there's lots of the data in this other group that is bigger. So there's a little bit of data that overlaps, but generally speaking, lots of one group is bigger than lots of the other group. So again, that's a situation where I could reasonably confidently say this group tends to be bigger than that group, because a lot of them are bigger than a lot of the others. What if they're a bit closer again? So in this case, there's a tail down the bottom, so a few people in this group are smaller than everybody else. The opposite, there's a few in this top group that are bigger. But there's lots of values that are the same. There's a lot of overlap between a lot of the data. So in this situation, we couldn't make the call. If the groups now are exactly the same, that tells me that no one in either group is bigger or smaller. So I definitely can't claim that one group tends to be bigger than another, because they all look very similar values. So these are the kinds of things we're trying to distinguish between. Let's go into a little more detail. When I look at a box plot, each section of my box plot contains 25% of the data. So the tail down the bottom, there's 25%. And the first half of the box is 25%, the second half is another 25%, and the top tail covers 25% of the data. So if we use this idea, we can form a rule called the 50-75% or half three-quarter rule. And the way it works is it says if I take one group and shade in 50%, so from the median down, shade in 50% of the top group. Now for the second group, I'm from the top down, I'm going to shade in 75%. And because I've got them overlapping, in this situation there is too much overlap. I can't make the call. There's a lot of these values that could be the same, so I can't say that one group tends to be bigger than another. Whereas for this second scenario, if I shade in 50% and then I shade in 75%, so I've shaded 50% of the top graph and 75% of the bottom graph, and they don't overlap. So there's 50% of the data in one is smaller than 75% of the data in the other. So this says that I could make the call. That is enough evidence for me to say that lots of this group is bigger than a whole lot of the other group. So that forms two specific rules that we're going to use. Rule number one says if there is absolutely no overlap of the boxes, then group A tends to be bigger than group B for the population, because remember, we're making an inference about the population. We're saying this is my sample data and I'm suggesting that in the population, so I could shade in here the box of the bottom group, here's the shading in of the box of the top group. Those boxes don't overlap, so that means I can make the claim that group A tends to be bigger than group B for my population. The second rule is what happens if they're a little bit closer. When do I change from making the call to not making the call? So this is rule number 2, and this comes from the 50%, 75%. So if the median for one of the samples lies outside the box for the other sample, then I can make the call. So if I draw a line for the median of the top group, and I draw around the box of the second group, they don't touch each other. That means I can make the call. They are far enough apart. So let's have a look at an example. Here's our problem. I wonder if the heights of boys tends to be taller than girls for all Year 11 students at St Kentigern College. So that's my population. Now here is a graph of the sample data, and we're going to use that sample data to make an inference or suggestion about the population. So we're going to use this rule about the median. So here is my line. I've drawn it through. That's the median of the females group. And now I'm going to draw a box around the males. And that median cuts through the box. So that means, with that scenario, I couldn't make the call. Let's just double check the other way around as well. So what if I was to draw a line through the median of the males and the box of the females? Again, it cuts through. So it's not separated. So I can't make the call. So when I come to write my conclusion now, I'm first of all going to say that I can't make the call because, and this is my justification, the median of the boys' height lies inside the box of the girls, and the other way around, the median of the girls' height lies inside the box of the boys. If one of them was outside the box, then I could make the call. So in terms of answering my investigation question, my inference is to say I can't make the call that boys tend to be taller than girls for all of the Year 11 students at St Kentigern College. So I've got a sample, and that sample I'm suggesting that I can't make the call for all of the students, that boys tend to be taller than girls. Thanks for watching.